All right, let's jump right into this explainer. Today, we are going to unravel a totally mind-bending reality of theoretical physics. We're talking about white holes, the cosmic fountains of the universe. Okay, so we all know about black holes, right? They're the ultimate cosmic trap. Just this inescapable gravitational sink where matter, light, information, basically everything gets sucked in and can't get out. But here's the crazy part. The math of general relativity actually allows for their exact opposite. Enter the white hole, a cosmic fountain. Instead of pulling things in, a white hole endlessly pushes matter and radiation away. It is effectively a time-reversed barrier. You can absolutely exit, but you can never, ever enter. Now you might be wondering, where did this wild idea even come from? Well, it actually comes straight from the math. Einstein's equations of general relativity are what we call time-symmetric. That means they function identically whether time is moving forward or backward. Back in 1916, when Carl Schwarzschild derived the very first exact mathematical solution for a black hole, physicists realized something huge. The math doesn't actually dictate a one-way arrow of time. If you run the clock backward on that exact same geometry, boom, you get a white hole. But, math on a chalkboard is one thing. Physical reality, that's a completely different story. And this is where we run into the second law of thermodynamics, which states that the entropy, or the disorder, of the universe must always increase. We all know the messy room analogy, right? Left alone, a room naturally becomes more chaotic, not cleaner. Well, a classical white hole effectively runs that entropy clock backward. It takes a singularity of infinite density and just spontaneously organizes it into matter, without any energy input. It literally violates the natural flow of time. And this right here brings us to a huge, fatal flaw, the inevitable death of a white hole. In 1974, astrophysicist Douglas Eardley showed that classical white holes are, well, hopelessly unstable. Here's why. While a white hole is pushing matter out, its positive gravitational mass is still attracting ambient dust from the outside. As just a tiny bit of matter approaches that horizon, it experiences an infinite gravitational blue shift. It piles up into this highly concentrated blue sheet of energy, and that massive accumulation instantly collapses the whole geometry. The white hole basically suffocates under its own gravity, turning right back into a black hole. But wait, despite that massive problem of classical instability, physicists couldn't just ignore the underlying math. And in 1935, it led to a massive breakthrough. You've probably heard of it, the Einstein-Rosen bridge, better known to the rest of us as a wormhole. See, the original Schwarzschild math suggested that a black hole in one region of space-time could theoretically be connected via a sort of spatial throat to a white hole in another region, meaning matter falling into the black hole could be spat right out of the white hole, maybe even in a completely different universe. So think of it like this. We've got three distinct cosmic players interacting here. Black holes trap, white holes eject, and wormholes connect the two. But there's a pretty big catch with wormholes too. Just like the white hole itself, a classical wormhole is highly unstable. Without some kind of exotic matter with negative energy, to hold that throat open, the bridge pinches off way too fast for anything to actually cross it. Any traveler trying to pass through would just hit the central singularity and be completely destroyed. No sci-fi shortcuts here, unfortunately. So let's be real for a second. If white holes are highly unstable, practically impossible under classical physics, and we have literally never observed one despite decades of searching, why do physicists still care? Why is this still such a hot topic in theoretical research? Well, to answer that, we have to shift gears. We have to move away from the bad news of classical instability and look at the fascinating, totally weird twist of modern quantum mechanics. The answer actually lies in loop quantum gravity. It's this incredibly cool modern framework that tries to unite Einstein's gravity with quantum mechanics. And in this modern view, the dreaded singularity at the center of a black hole, that point of infinite density, might not actually be infinite at all. If spacetime itself is discrete, meaning it exists in these tiny quantized chunks, then there's a fundamental physical limit that prevents matter from collapsing endlessly. And that limit? That sets the stage for a truly spectacular transition. Let's break down how this quantum bounce would actually work. First, picture a dying star collapsing, forming what looks perfectly like a standard black hole. Second, that collapsing matter hits the absolute maximum density allowed by quantum physics. It forms what's called a Planck star. It physically cannot compress even a fraction more. So third, it rebounds. It bounces outward, emerging as a white hole. It's actually a lot like dropping a rubber ball. But because of extreme time distortion, this bounce takes only microseconds for the matter inside, while for us on the outside, billions of years pass. Which means the black holes we're looking at today might actually be white holes, just waiting in slow motion to explode.
And this is where things get really exciting, because this framework gives us a tantalizing way to potentially observe them in the real world. Could white holes explain our most violent, unexplained cosmic anomalies? Take gamma ray bursts, the most energetic explosions in the universe. They're usually linked to collapsing stars. But back in 2006, astronomers detected this massive burst, GRB 060614, with absolutely no associated supernova. It just happened in an empty void, a spontaneous, massive ejection of energy and matter from utter nothingness, perfectly matches the theoretical profile of a white hole eruption, a small bang, if you will. Now take that idea and scale it way, way up. Astronomers Alan Rutter and Shlomo Heller actually propose that these isolated gamma ray bursts are exactly that, small bangs. Single, spontaneous ejections that perfectly bypass the classical instability problem because they expel everything outward before any ambient matter can pile up and crush them. And if a small bang is a white hole, well, you have to ask the ultimate question. What about the Big Bang itself? This singular eruption that seeded our entire cosmos looks remarkably, almost identically, like a supermassive white hole. Okay, brace yourselves, because this next concept is truly mind-blowing. It's rooted in something called Einstein-Cardin theory. By incorporating the quantum spin of particles to prevent those nasty infinite singularities, this theory suggests that instead of crushing into an infinite point, matter inside a black hole bounces and expands into a brand new closed baby universe. And to anyone inside that baby universe, that initial rapid expansion would look exactly like a supermassive white hole eruption. Think about what that means. Our entire universe could currently be expanding inside the white hole interior of a black hole, which is located in a completely different, older parent universe. So, what does this all mean for us? It completely flips our perspective. White holes went from being this quirky mathematical artifact to an unstable classical impossibility to potentially the very mechanism that sparks the birth of entire universes. It fundamentally changes how we view the origin and the ultimate fate of the cosmos. So I'm going to leave you with this lingering thought to chew on today. If our Big Bang was actually a supermassive white hole eruption, what black hole in what parent universe gave birth to us? Keep wondering about that one, and I'll catch you in the next explainer.